So I already told you what the problem I want to discuss with you today is that we have two transmission lines which are connected using inductance. For example, this could be the equivalent circuit also for a connector between two transmission lines of 50 ohm, and due to the connector there would exist a series inductance. So the question is now how to find the scattering parameters of this situation. And perhaps so you have here, in principle we have here port 1 and here port 2, and of course the inductance itself is a lumped element. This means we don't account for its physical size. So perhaps if you have a problem like this, the easiest way to start to solve a problem like this is to start with the S parameter as 1,1. So we know that S parameter as 1,1 is in principle the reflection coefficient. Perhaps I call it RL, which I see into port 1 here. So this would be RL, but only if port 1 must be matched. Well, I write here no, sorry, not port 1 must be matched. Of course, port 2 must be matched. Under these circumstances, this is the S parameter as 1,1 I see into our circuit here. And of course here we have transmission line. Perhaps I cut this transmission line here, and if I have to match port 2, what do I have to do? Can somebody answer this question? If I want to match port 2 now, what do we have to do here with this transmission line? Somebody an idea?
We match a load impedance with ZC.
Yeah, we have to terminate this transmission line with a load impedance which is equal to ZC. But if you terminate a transmission line with its own load impedance, then also you can think that this load impedance is transformed into this plane. So we will get a different equivalent circuit. And it looks like this, that you have here our transmission line ZC. Then we have here the series inductance as a lumped element also. And then here we have a load impedance which is equal to ZC. So the overall load impedance, with which port 1, here you have port 1, and this is in principle the overall load impedance ZL. And we know now, if I want to calculate RL, we can use the equation that RL is equal to ZL minus ZC divided by ZL plus ZC. This is how we can always calculate the load reflection coefficient. Again, very important, S11, if I consider a two-port, S11 is equal to the load reflection coefficient if port 2 is matched. This is very important because this will change now, so we can switch from this to this equivalent circuit. So are there some questions perhaps concerning this step? So, and the only thing what you have to think of is now to calculate or to write the equation for ZL, and you see here that ZL is just the series connection of the reactance or of the impedance of L, which is J omega L. This is the impedance of our inductance plus ZC. So, and of course you have to insert this equation now here for the load impedance, and we will have then RL is equal to, I write it like this, J omega L plus ZC minus ZC divided by, and of course you see here we will have 2 ZC plus J omega L. So you see here these two will cancel, and the final result for the load impedance will be RL, it's equal to J omega L divided by 2 ZC plus J omega L. So this will be the equation for the load impedance. Could you follow this calculation, or are there some questions? Of course, this would be now also, I can delete this also and can say, of course, this is, according to this equation, this is S11. So perhaps I first write S11 again here, and then I delete this equation here. So we get for S11, we will get that is equal to J omega L divided by 2 ZC plus J omega L. So this is our equation for S11. So we, of course, now you see here it's still a quite complicated expression. So I want to, perhaps we first calculate the reactance of L. So XL would be omega L, and in our case it would be 2 pi 10 to the power of 8 1/seconds, and we have here times 20 10 to the power of minus 9. And if you calculate the value, then you will get as a result XL is now 12.6 ohm roundabout. This would be XL, the value. And now you see here that we have ZC is 50 ohm, and 2 times ZC would be equal to 100 ohm, and there you add now plus J 12 ohm, and we can do an approximation. And of course, we can then say that since this term is much lower than this term, so the absolute value will essentially not change, and we can say S11, we can use an approximation. This is J omega L divided by 2 times ZC. And this is J. Now we see this is 12.6 ohm divided by 100 ohm. And so you get as a result S11 is approximately J 0.126. This would be the value for S11. So could everybody follow, or are there some questions? So there are still no questions. Then I can go on and do in the next step. You see that we have, of course you can interchange port 1 and port 2 here without changing the network. So if I would say this is port 2 and this is port 1, then so that network does not change. So we can also conclude that this is equal to S22. So this is also equal to S22, and from this we found now that we have S11 and S22, and I'll write this here. So from this point we can say S11 is equal to S22 is equal to J 0.26. This will be the value of S11 and S22. Are there further questions, or are there some questions?
Sorry, why is S11 equal to S22?
Because you see here, if you have a look to the circuit, delete this. So here, this is a transmission line with ZC, and you see here, if you would name this port 2 and this port 1, the circuit itself will not change. So you can interchange port 1 and port 2 without changing the circuit. So the electrical behavior of the circuit must be the same. So this is why S11 is equal to S22. Did this answer the question?
Yes, so this is like symmetrical, right?
Yeah, due to the symmetry. So if you interchange, due to the symmetry, the both are the same.
Yes, thank you very much.
So now we can use another property of this circuit. My question to you: what is the special property of the inductance here? If I consider losses, for example, can you answer? Can somebody answer this? Or what does an inductance do from this physical point of view, or also from the electrical point? Physics and electricity are explained, or physics explains electricity. So again, my question: what does an inductance do in an RF circuit, in a pure inductance?
like its property in the matching circuit, or just its physical property in general?
Yeah, its physical property in general.
It stores magnetic energy.
It stores magnetic field energy. This is correct. So what it does not dissipate energy. This is very important. So what do we have here if I say this is our two-port? What about the losses of this two-port?
So this two-port has no loss?
So this two-port has no losses. And this results in the fact that we can now use the conditions which apply to a lossless two-port. And I turned this, for example, the absolute value condition, or and it's easier. So if I have a two-port, I can write this two-port like this, as 1, 1, as 1, 2, as 2, 1, as 2, 2. This is the general S matrix which describes a two-port. But if I have the absolute value conditions, you should remember that you just have to take the absolute value of this plus the absolute value of this, and this must be 1. And also the absolute value of this plus the absolute value of this must be 1. So this I call the absolute value conditions of a two-port, of a lossless two-port. Of course, this is only valid for a lossless two-port. And this is how you can easily remember these two equations. So from this point of view, we can say that, for example, the absolute value, the absolute value of S11 absolute value square plus the absolute value of S21 absolute value square must be 1. Or I can say that S21, the absolute value of S21 is equal to the square root of 1 minus S11 absolute value squared. So this is the condition, and from this equation we easily can calculate S21. It will be 1 minus, and we have here 0.126 squared. And if you calculate this value, this is 0.126 squared minus plus 1, and you take the square root, and then you will get that S21 is equal to 0.992. This will be the absolute value of S21. And of course, you see here, there are two things. We also can say, you learned that, well, I told you in the videos, as soon as I have a passive two-port, which means there are no elements like transistors in it or so on, then we have a passive two-port, and then the passive two-port is always reciprocal. This means S12 is always equal to S21. But also you could see here, as according to the absolute value condition, since S22 is the same as S11, they are both the same. So we see also here that we have that this is equal to S12 absolute value. So now we in principle have the result for our scattering matrix. We could say now our scattering matrix is equal to J 0.126, and here I just write 0.992. Here I can write 0.992, and here again J 0.126. Of course, you see here I just inserted now the absolute value of S21. So in principle I should perhaps include here a phase. So at the moment I don't know, but since we don't have any physical or physical size of the inductance, we can think that, of course, we just take the value, the real value of this, and my question is now, can we prove that this is okay? What can we use to prove that this S matrix now would fulfill all conditions? Who remembers which further condition S matrix, or any S matrix must hold if it's lossless? I have to write like this: equation 3.11 in the lecture notes, and this equation is called phase condition. So beside the absolute value condition I already introduced, or I applied, a lossless two-port must also fulfill the so-called phase condition, and the phase condition reads that S11 times S12 conjugate complex plus S21 times S22 conjugate complex must be 0. This is the so-called phase condition, and in principle you can remember the phase condition. Perhaps I'll write here again. How can I remember the phase condition? So this is again the S matrix, and I must in principle take this Coulomb vector times this, the conjugate complex of this Coulomb vector must be 0. So this is if I think this is a certain Coulomb vector and this is a Coulomb vector, then the dot product between these two Coulomb vectors must be 0. This is how to remember these phase conditions. And of course now we can prove the phase condition here. And you see you have to take S11 is J 0.126 times S12 conjugate complex, but this is the real value. This means we have to multiply with 0.992 plus, now we have to take 0.992 times the conjugate complex of S22, but this is J, so this would be minus J 0.126, and of course this is 0. So of course we can in principle tick now. This means we have the phase condition is fulfilled, that again results that this is the correct, or shows us that this is the correct S matrix of our series inductance at 100 megahertz.